This is Suman from Midas. So I'm a structural engineer working at Midas R&D Mumbai. So today I'll be talking about this topic, which is balanced cantilever bridge camber control. So I really want to give a big picture about the topic. How do you get the cambers? How do you calculate them? And how do you go about controlling the camber in balanced cantilever bridge? So I'll be providing you the insights for the camber calculations. So mostly I'm going to hit the title, that is the camber control, not going much into the balanced cantilever bridge modeling. So if you want a balanced cantilever bridge, how you wanted to do in Midas, so you can watch some of our YouTube videos or the tutorials, the inbuilt tutorials, you can go through them. So mostly I'll be talking about camber and its control. All right. So first, regarding the balanced cantilever bridge, just an introduction. So this is how a balanced cantilever bridge would look like. So you'll be having a pier, and the pier table would be constructed first, and then segment wise the deck would be erected. Like the left and the right would be simultaneously erected, so that there won't be huge unbalanced movements. So you don't want it unbalanced movements to be created at this pier locations. So you go one by one simultaneously on the left and right side of the pier. So that's the balanced cantilever way of construction. So if you see into that, so there are two methods of this deck construction of balanced cantilever bridge. One is cast in place, where the formwork is put in and it's connected to the previously installed concrete and allowed to cantilever freely. And the next, permanent reinforcing steel and the supports, all those would be installed, and finally concrete is poured and it's cured. So that's why one segment would be cured in this side and this side, and they go about the next segment construction. So that's cast in place. And there is another method called precast segmental deck erection, where the precast segments would be lifted to the position and they would be adjusted, and thereby they will be pre-stressed, and the new segments would be formed, and the cantilever erections would be performed. So these are the two methods of deck erection sequences that generally follow for balanced cantilever bridges. One is cast in place, another is precast segmental. So if you see the construction stages that you define in Midas or any other program, this is very much required because the structure evolves. Hence, the structure analysis should be performed for each stage, and the sectional stability for each stage must be checked. As you see in this erection sequence, so you have a pier table and these segments would be casted one after the other, and the tendons would be stressed. Like you will be having the cantilever tendons or the continuity tendons. So to consider time dependent characteristics for the concrete, and we need to consider the relaxation of the pre-stressing strands precisely. So the accumulated analysis results from the preceding construction stages are very much required for each subsequent construction stage. So we'll be carry forwarding the analysis results to the next stages. So that's how you make the accumulative construction stage analysis results. Alright, I hope this is very clear. So let's go into the next slide, where the main deformation problem is put on, where you have the factors that are affecting the deformation prediction. So to provide a camber, so first question is, why do you provide a camber? So the camber is required to counter the deformations which are acting because of lot of parameters. So to counteract the deformation and to provide a smooth camber where the traffic that is moving onto the bridge and the serviceability are not affected, and the rider on the bridge feels comfortable, so you need to provide a pre-camber. So before getting into the pre-camber, you should calculate the deformation. So the deformation prediction is very much important. So there are a number of factors that will be affecting the deformation prediction. So first one is creep. So as you know, creep is a time dependent deformation of the concrete under permanent loads. So mind you, this is stress dependent. So the time histories of the stresses and the time becomes the important factors for determining the creep. So this is the complicated behavior of the concrete material itself. And there's also one other material behavior like shrinkage. So this is a time dependent strain measured in an unloaded and unrestrained specimen at constant temperature. That's what you call it as shrinkage of concrete. So this is stress independent, whereas the creep is stress dependent. So next is the pre-stress losses. So you also need to accurately capture the pre-stress losses that happens with the time, like the frictional anchorage slip. If you have a post-tensioning system, then you'll be having the relaxation of the pre-stressing steel. So all these factors will heavily affect the deformations. All right, and next is the construction process. So as you know, the balance cantilever bridges are erected in this sequence. So this construction sequence and then chronological order of the casting of the segments is very much required, and simulating the segment wise construction procedure according to the actual true erection sequence from the site is required. So the complex loading history needs to be considered. Coming to the concrete material, so nowadays most of these bridges are using high strength concrete, or they might be using lightweight concrete. So these also affect the creep and shrinkage models that we will be considering. So I'll be showing you some of the creep and shrinkage models in the coming slides, where this concrete material will affect those models. And there would be time delays. So sensitivity of the deformations to the variation in construction schedule and the procedures and the time delays. So you also need to account for this, because the creep and shrinkage, all these parameters are time dependent. So if you have any time loss, so you need to take care about that in the analysis. I hope this slide is clear. So these are the main factors. These 6 factors will affect the deformations and the predictions. So we need to take care about these factors. So because of these factors, what happens if you have a segmental bridge, balance cantilever bridge? So you'll be having excessive sag at the middle. So if a rider goes here, then he'll feel very discomfort and the serviceability would be heavily affected. And if you see the sequence where from the left side you are erecting and from the right side you are erecting, there can be a mismatch. There can be a deflection mismatch where uneven connection of free cantilevers can happen. So you also need to predict this deformation and provide the pre-camber so that these two will meet at the most accurately at the same location to provide a smooth transition. So the so how to solve these 2 problems? That's providing a pre-camber is the solution. So pre-camber by definition is a designed elevation of the span plus the necessary overheight. So the design height can be straight and the necessary overheight is what the pre-camber can be. So let's go to the next slide. So what about the deformation solution that is provided by Midas? So in Midas, we always strive to provide innovative solutions which are practical and reliable. So first one, we have this factor called creep, shrinkage, and the compressive strength variation. So these heavily affect the deformation prediction. So we have in the program an accurate long-term prediction models for creep and shrinkage as per the code like CEB, FIP or ACI or any or ASTO or IRC also. So we have as per code, and you can also give the user defined values like for the creep coefficient and the shrinkage strains. So the program will consider this creep coefficient and the shrinkage strains along with the compressive strength variation in the construction state analysis. So you can refer to this very interesting paper. He's a pioneer, he's a researcher who started this creep and shrinkage prediction models, Basant 2001. So you can refer to his papers. So compressive strength variation based on the maturity of the concrete member in the analysis can also be defined with respect to the code, or you can have a user defined values. Next, in the program, we have this construction stay analysis. I hope most of the people are aware about the construction stay analysis in Midas Civil. So we'll be performing the construction stay analysis accurately, taking into consideration all the factors which are involved in the balance cantilever construction process, like the formwork load, how the segments are erected, and what's the time schedule of the two piers. All those details we'll be including in the construction stay analysis, and then thereby we can accurately capture the pre-stress losses, even the relaxation loss of the tenants. So Midas Civil allows us to specify the construction stages and their composition in detail to reflect the true erection sequence of the construction. So these two things are taken care. So we also provide camber tools in Midas Civil, especially to cater the balanced cantilever cambers. So one is the tangent displacement calculation, and the next one is the construction and the manufacture camber graphs, and the tables can be readily outputted. And we can also provide this camber into the construction stages and check whether the desired level is reached or not. So I'll be explaining you this in detail in the coming slides, right? So I wanted to give a brief idea about how creep and shrinkage is calculated in Midas, the background. So you see this graph, which is the shrinkage would be occurring when the concrete is poured. Suppose after 3 days, if you start thinking that the shrinkage would appear, and then you'll have the immediate strains, the elastic strains, and then with respect to the time, there can be a creep strains that would be accumulated. And with the unload of some loads, there can be an immediate recovery of the creep, immediate recovery of the strains, elastic strain recovery, and the creep strain recovery. So this is the overall figure that speaks about the creep and shrinkage. So coming to Midas, Midas uses a FEA approach with a time step method for calculating the creep strains. So the total strain here has a components due to elastic and creep strains, due to shrinkage strains, and also due to thermal strain. So this thermal strain will come into picture when you provide the thermal inputs. All right. So coming to the creep strain, so creep strain is the integration by the stress history. So you integrate this whole stress history in a particular time period, like the construction duration from 0 to T days of this construction duration. You integrate the stress history with respect to the specific creep. So the stress is applied in time steps, keeping everything, every other thing constant in a particular small time step, as you can see in this stress history curve. So then there would be specific creep curves that would be generated with respect to the time. At each time interval, the specific creep curves can be obtained, and then you superimpose this. So you use linear superimposition method to combine the stress history with the specific curves to get the total creep strain. So it is an accumulative effect using the linear superposition, and the total creep strain is calculated. So the creep deformation here are summed over increasing stress history. So you'll be calculating this incremental creep strain, and then you will be adding upon that to get the total creep strain. So comprehensively, the details are given in the analysis manual of Midas Civil, so you can refer to that. This is all about the creep. Coming to the shrinkage, so you'll be having two type of shrinkage strains. So the total shrinkage is the addition of autogeneous shrinkage plus the drying shrinkage strains. So this is straightforward. So you'll be getting this formulas, everything from the code, or you can give user defined values to the program. So coming to the big question, why construction stay analysis? So I put this slide to explain you the difference when you do the construction stay analysis and without construction stay analysis. So if you see the bending moment diagram due to self-weight only for a balanced cantilever bridge like this, where the simultaneous analysis is performed, not taking into consideration the sequence, the construction sequence. So you'll be getting this bending moment diagram. So you can see here, there is a sagging moment and the hogging moments. When you take into consideration the sequential analysis, there's a whole change of pattern of the bending moment diagram. So there would be a lot of hogging moments here, and the sagging moments would be reduced. So this is what needs to be reflected in the program. So we always need to bear in mind that we are analyzing a representative model but not the real structure. Because the model is wrong, then your results are wrong. So you should always take care about how the true erection sequence is taken place in the site, and you need to most probably simulate the same things in the program to get the correct results for the design. So if the actual construction stage is halted for any reason, then additional time steps can also be inserted into the respective stages that I'll be showing you in the demo. And I also want to point out that the weight of the traveling formwork is also can be taken into account in the simulation because it would be having a significant influence on the total deformation. All right. So let's get into the two types of camber. That is, one is construction camber, another is manufacturing camber. So as you know, the pre-camber curve is the short plus long-term deflection curve with the opposite sign. So it shows the necessary overheight for each segment over its design elevation where the formwork has to be positioned. So you see here, so you have this construction camber diagram. So if you have a cantilever, suppose which is divided into three segments, which would be erected in three stages, suppose. First stage is only this cantilever portion. Second stage, this would be stitched to the rest of the segment. And third, this part would be stitched to the rest of the structure. So if you see the deformation profile, so first this segment would be deflecting. So this is because of the load. Suppose a 10 kilonewton load is 10 kilonewton per meter load UDL is applied over here. So not excluding the self weight. So that because of that load, if the deflection is delta 1 1, because of the loading at 1, there is a deflection at 1th position. So if you draw a tangent line over here, so you will be getting delta 2 1 and delta 3 1. Because of the loading at 1, there would be a deflection at 2 and at 3. So these are tangent displacements we call. Coming to the stage 2, when this segment is added, then delta 2 2 is appeared. And the segment is stitched at this location, starting from this location. So because of this load which is acting 10 kilonewton per meter only in this segment, there would be a deflection at delta 1 2 because of the load at 2. So this is delta 1 2 and similarly delta 3 2. Similarly, because of this load which is acting in this segment, there would be deflection at these points as well. So these are all nothing but the current stage displacements. So because of this current stage, there is a displacement here, and because of this current stage and the current loading, there is a displacement which is would be occurring. And similarly at this part. So if you see the summation of the deflections at node 1, if you see at here, so it would be the addition of this deflection plus this at the 1th location at node 1. At node 2, we will not be adding the tangent displacement, but we'll be adding this two displacements because it's a construction camber. So I'll be telling you why you will not be adding this in the next slides. At node 3 for the construction process, you take into consideration only delta 3 3. So if you see the construction figure, if you draw it, if the camber, if you draw the deflections in the opposite sign, so you'll be getting this curve. So this is what a typical curve would look like for a construction camber. So due to the nature of the segment-wise construction in balanced cantilever bridges, the deformation diagram will have the discontinuities at the segment borders. So irrespective of the deformations of the already existing neighbor segments, when a new segment is built in place, it has zero deformation at time 0 and before loading. So this generally corresponds to a situation in reality that the formwork for the subsequent cast segment is set at the prescribed elevation when the existing part of the cantilever has already undergone deformations. So you'll adjust this cantilevers before erection. So that's why you don't add this tangent displacement, because you adjust this deformation this erection of this part starting from here at these locations. So while because of that adjustment, this can only be possible in cast into segments where the formwork can be adjusted and the concrete would be poured for the next segments. So this is would be a typical example, would be a balanced cantilever bridge with a cast in situ segments. All right. So coming to the values, if you see the values here, suppose you got these values over here. So these are the red ones are current stage displacements, and the subsequent, the concurrent displacements are given in blue. So this would be the final construction camber values, which are nothing but the deformations of the construction. At the end of the construction stages, you'll be seeing this in the program. So let me jump into the program now. I'll show you one model where this has been a trial model I have developed. So you can see this is the cantilever. So if you see the stage one, so this part is like for 5 meters, and this is the section. Coming to the CS2, there would be another segment of 5 meters which would be added to the rest of the structure. Similarly, CS3. So I'll perform the analysis and I'll go to the results to check the deformations. So if I see the deformations, so I'll go to CS1, I'll turn on the legend, turn on the undeformed shape, turn on the values. So you can see 4.789 is for this segment. Coming to the CS2, this is 64.965, and at this location, so it's 27.017. Coming to the CS3, so there is a kink over here. This is 257. So to check the current stage displacement, so you have this option, current step displacement. For this to appear in the program, you have to go to construction state analysis and turn on this save output of current stage. All right. So then this option would be appearing. So you can select that, and if you go to CS1, so the current step and the stage displacements are same for CS1 because there is no changes in the construction in the structure. So in CS2, if you see, there is a change in the structure. This segment is being added. So in the current step, only because of this loading which is occurring in this 5 meters one, there is a subsequent deformation here. But if you turn off this and check, so this is the addition of the previous displacement which happened in CS1. So that's why it's 20. That's why if you see here, the previous displacement would be added to this. All right. So similarly in CS3, you can turn on the current step displacements and get these displacements, which are because of the current step. This is 257, and the concurrent displacements are these two displacements. Now, if you turn off this and click apply for CS3, there would be a summation of all these three values to this node and all these two values, not taking into consideration of this tangent displacement. So you'll be getting this 204, and this would be carry forwarded. So this is what the construction camber is. So in the program, if you don't turn on this current step displacement and click apply, so these are nothing but your construction camber displacements, which are actual at the end of the construction stage, your deformations. All right. So now let's go to the next type of camber, which is the manufacturing camber. So this is used for the situations where the next element would be activated with J node, but taking into consideration the tangent displacement also. So if you see this, the same figure is repeated here. So you have these deformations and their profile. So if you see at node 1, so this is the summation of these three. Coming to node 2, this would take into consideration these tangent displacements which are given in this dot. So these three deformations are this tangent deformations. So we'll be considering these tangent deformations also for the deformation calculations for manufacturing camber. So for node 3, this is the summation of all these three values. Okay, so to see the real displacements, this is what we call as real displacements. So generally for precast segments, so you can't adjust these segments individually like what you do in a cast in place formwork adjustment. So that's why you have to start from here. So that's why you need to consider this deflection tangent displacement also into consideration when you are dealing with a precast segmental bridge. So if you see the manufacturing curve, this is how it looks, manufacturing camber curve. So let me show you those values. So these are the values that you got after the construction stages, but you wanted to include the tangent displacements also. So these are the tangent displacements the program will give. So if you consider these things, so you'll be getting this final values which are different from the construction camber values because you are adding this tangent displacements. So to get this tangent displacements, so in the program you have to go to construction stage analysis control and turn on this initial tangent displacements for erected structures. Alright, then the program will give you this option of stage step real displacement. So at CS1, so you can check this. In CS2, there is a change of deformations considering the tangent displacements, and in CS3, this is the value. Alright, I hope everything is very clear. So let's proceed. So these are the tangent displacements and you'll be getting the manufacturing camber accordingly. So in Midas, as I showed you, there are three features that are available. One is this construction stay analysis control. So where you can directly get this tangent displacements and you can apply this camber displacement to construction stages. I'll be showing you this feature again. Coming to the general and FCM camber. So if you perform the analysis, then you can see these two options that are available in the program. So one is this FCM camber control and other is general camber control. Alright, let's get into the program now. I'll show you this in detail. Suppose you have a balanced cantilever bridge like this. So we have the stage 1, stage 2, all these erections which are going on in a balanced cantilever fashion, and there is a stitch in CS15, and if you see this CS17 where the 10,000 days duration is provided, not changing any of them, is to capture the creep and shrinkage long-term effects. So I have performed the analysis to save time. So these are all there in the works tab. You can see all the boundary conditions and the time dependent material properties. So as I mentioned in the slides that you can give the user defined or you can select the code for the creep and shrinkage calculations. So here you can select the CEB FIP code. All these codes are available and you can go to show calculation results to check your creep coefficient and the shrinkage strain. So this is only for checking. The program will take its own creep coefficient curve based on the construction stages because the duration, start loading, end loading would change for each construction stage and it's an accumulative process. So this is only for the verification that the program shows you this result. Alright, so you can you can specify the user defined as well. And similarly the compressive strength variation. So for the superstructure I've selected CEB FIP 1990 and this is the compressive strength variation curve with respect to time. So these are the time dependent material properties that I have given in the program. Alright, so let's go to the results now. I'll go to results I'll go to deformations. I'll go to this stage which is suppose CS1. I'll click apply. So this is the deformation in Z direction. I'll turn on the legend. I'll turn on the undeformed line. So this is the dead load deformation with including the pre-stress. So this is the summation deformation. So if you want to see the dead load deformation, this is the dead load deformation. Including the pre-stress effect, creep and shrinkage effect is nothing but the summation one. So let's see the summation results. So this is how the summation deflections, which are nothing but your construction camber. Alright. So till CS15, so this would be the deformation profile changes. And at CS16, there is the key segments that are coming up to connect this FCM ends and this intermediate one. So you can always switch to the current step displacement and check, because of only the current loading of this construction stage, how is the displacement profile. And similarly, you can take into consideration the tangent displacements and check the deflections. So you can turn on the stage step real displacement and check how is the real displacements that are going up. So if you see in CS15, there is uh, a difference in the tip of the cantilevers. So this is regarding the stage step real displacement. I hope everyone is clear about this current step displacement and the construction's stage displacement and the stage step real displacement. Alright, so now we accurately predicted the deformations for this balanced cantilever bridge, taking into consideration all the formwork load, all the erection sequence, time dependent effects, everything has been considered. The pre-stress losses are also being considered. So we assume that the deformations are with sufficient accuracy. So we'll proceed for providing the camber. For that, we go to the camber and click on this FCM camber. So go to FCM camber control. So the program will ask you for this groups, for this element group of the bridge girder, support node group, and the key segment element group. So I'll go to group. So I see that no groups are defined here. So I'll unlock the model. So I'll define a bridge girder group. So I'll select the superstructure and I'll drag and drop this bridge girder group. So you see node 83 nodes and 82 elements have been assigned. So you can double click and cross check. So I'll add another group which is your support node. So if you see here, for a balanced cantilever superstructure, we are connecting this with a rigid link. So these nodes are your support nodes. So we need to select these as the support nodes because your cambers would start from here. So I'll select this support. So these support nodes are selected. I'll drag and drop. So these are 6 nodes. So actual supports are this ones. Now I'll add another group which is key segment. So I'll select all these key segments. I'll activate them. Select all. I'll just drag and drop. So the key segments, support nodes, and the bridge girder groups are created. Now no need to perform the analysis again. So I can go to Camber, FCM Camber, click on this FCM Camber control. Now I'll select the bridge girder group which I have recently created, and the support nodes and the key segment locations. That group, I'll click OK. So now I can directly go to FCM Camber and click on FCM Camber Graph View. So you can select any load case that you want, either for dead load or all this FX summation. So I'll select summation that you generally take, click OK. So this is the FCM camber for a balanced cantilever bridge. So this is the construction camber for a cast in place balanced cantilever construction method. So you generally take this camber, construction camber, into account. So you see at this two pier locations and at the intermediate key segment and here at the key segments there are kinks. These are all because of the adjustment of the form work. So you can zoom in the program. So you can right click and zoom out and check these values. So you can see this is the node numbers and these are the camber in mm that you provide. So I'll zoom out all. So this would be the opposite of the deformation. Let me cross check that. So you can go to CS15, which is the end of the construction stage. Go to last step, click apply. So this is the undeformed one. Let me turn on the nodes. Yes. So see here, this is coming down here and you provide upward camber. So this would be the opposite of the deformation. Alright, I hope the FCM camber is very clear. Coming to the general camber, you also have this general camber control. So this is for any other type of bridge. So for a balanced cantilever bridge especially, we have provided a separate FCM camber and its FCM camber table also. So you can turn on the table and check the values. So in the nodes, so you see at the 7th node, so in each construction stage the camber needs to be provided. So you can get this in terms of pages. So as the columns are huge, like the length of the bridge is huge, so you have this in pages. So you can directly copy paste this in the Excel and you can use it and cross check them. Alright, so this is the camber tree. So you can get these values. So these are nothing but your deformations. Alright, so let's go to the general camber. So in general camber, this is for any other bridge like a FSM bridge, like full staging method bridge where you need the camber to be considered. So then you can select this direction of the construction and select your bridge girder group. Okay, and then you can get the curves. I'll go to general camber and click on general camber graph. So here you will be getting the construction camber curve as well as the manufacturing camber curve. So you can also get in tabular format. So this is the construction camber tree and this is the manufacturing camber tree. So these are all the camber values where the tangent deformations are also taken into consideration for the manufacturing camber. Alright, so I hope these two options are very clear. Coming to the next option we have is in Midas we have this camber for construction stages. So you can go to this option load construction stage and click on camber for CS. So you can directly input the camber to the construction stages. So I'll close this tabs. So I'll go to load, click on camber for construction stage, and here you have generated the FCM camber values beforehand. After the analysis and after this grouping, you got this FCM camber values. Now if you wanted to provide this to the superstructure, so you can go to initial view, just lock and unlock. go to construction stage, Camber for CS. Now I'll select the bridge girder group. Now I'll directly select this deformation curve, deformation camber, or you can specify the user defined maximum camber, start and end node you provide, and then you give the maximum camber, so the program will interpolate the in between cambers, or you can actually specify for each node what is the camber, so that these options are all there. So when you pick this deformation camber, the previously calculated FCM camber values would be automatically provided at their respective node locations. So I'll click apply. So you can click this three dot button to check the camber values. So these are all the values that have been obtained from the results. So this has been applied to the respective nodes at the in the construction stages. All right. So for this to check, you need to go to analysis, go to construction stage. So the program needs to apply this camber displacement to construction stage. So you have to turn this option. We can rerun. Generally, you don't need to rerun because you can always keep all those options turned on. And once you perform the analysis, you can adjust the cambers. But here I forgot to tick in that parameter. So it will just take a couple of minutes. Yeah. So you can appreciate the solver speed as well here. It just took 30 seconds. That's a great news. Okay, I'll go to deformation. I'll go to end construction stage, summation, click apply. So this is the deformation, and you can see this current step and the stage step real displacement. Now when you turn on that the parameter that in the construction stage analysis control, so you'll be getting this option as well, where include camber displacement. So the deformation curve, the figure will show you including the camber displacement. So let me turn on the legend, click apply. So you see the deformations which are in DZ. So the camber I've applied only in DZ direction. So in the last step, so you can see it's almost straight. So the deformations have come up to the level that we required. So this is how you can directly apply the cambers to the construction stages and check. Alright. So let me get back to the presentation. Let me summarize what we have discussed. So first is this parameters, where you'll get to know all this initial tangent displacements and applying the camber displacement to the CS, where you can specifically generate the FCM camber as well as the general camber. So you can get them in the graph or in the tabular format directly, and you can apply this to the construction stages. So application of pre-camber to CS stages, you can bring the superstructure to a desired level and cross-check in each construction stage whether you are satisfying it. All right. So I hope I have addressed many issues of Camber. Hope you enjoy the presentation. Now I can take your queries. So you can type in the questions box if you have any queries. You can type in the questions box. Yeah, this video would be put up on the YouTube, so you can watch. So some of the people are asking regarding this presentation will be shared. So the video would be put up and the slides will also be kept. Yeah, I'll share the slides with you. So if you have any questions, you can type in the questions box. Okay, thanks. It was nicely explained. Okay, thank you. So one question from Vijay Kumar, it's that when the shrinkage law is taken into account, whether it's 3 days or 10 days. So if you see in the program, so you can uh, go to the properties and go to this creep and shrinkage. And here you have this days that you give, age of concrete at the beginning of the shrinkage. Whether you wanted it to be 3 days or 10 days is up to you. So you can select the start age of the shrinkage. All right. So one more question from Manuel. He's Mr. Manuel. Like, are the formwork travelers or lifting frames included in your analysis? So we have given a full freedom for you to manipulate your construction stages. So if you have any formwork or lifting frames that are especially for your bridge project, you can include that in the program. Suppose in CS2 there might be here we have taken into consideration this loads. So you generally apply it as a nodal loads. So you can manipulate these values according to your direct train loads. So you can actually simulate the true erection sequence of the balance cantilever bridge in the program. So I'll go to this creep shrinkage curve. So it's with 3 days. Yes, another question, the follow-up question that you see only 10 days. So when you turn on this shrinkage, so I can give this 3 and click redraw graph. Alright, so I can change this and check. But the program will take this value internally. This is just to show you the curve and its behavior for this parameters. Okay. So another question from Himanshu, like Mr. Himanshu, that the difference between manufacturing camber and the construction camber. So this is a bit confusing. So I'll try to explain in simple words. So if you see the construction camber here, so you got these values from the program. So in the construction camber, you don't account these tangent displacements. These three values which are there, you don't consider. So because of this construction sequence, there is a change in deformations. So that you will be considering without considering this tangent displacements. That is called as construction camber. So you can see this formula. But if you see in the manufacturing camber, for this displacement at this node 2 location, you also will consider these green ones, which are nothing but your tangent displacements. So generally in precast segments, you don't have the adjustment. You don't have that allowance to adjust this tangent displacement. So that's why you need to consider this in the camber. So that's why it's called as manufacturing camber. All right. There's another question from Mr. Rakesh. What is meant by sequential analysis and simultaneous analysis? See, simultaneous analysis is nothing but you're not considering this construction stages. Just you are considering this bridge and applying all the loads, and you'll be getting a bending moment diagram, which is nothing but your continuous bridge and structure analysis. So in this sequence, you have a difference. So that's what I explained in this slide. Yes. So this is without taking into consideration the construction stay analysis. This is with construction stay analysis. So there would be a difference in the bending moment pattern. Alright, there are a lot of questions coming up. Actually, we are running short of time. So if you have any queries, so you can write to us at